So moving on, we have come to the topic modulation and demodulation, which is probably one of the most important new concepts in communication systems, and this is something which most people study in their engineering education as well. And we talked about the upper sideband, the lower sideband, and all that previously. But here we'll be looking at them in more detail. We'll also be looking at different kinds of modulation. So let's begin.
Yeah. So here modulation and demodulation. First, let me tell you what modulation and demodulation are. So superposition of the message on a high frequency carrier. Remember, it has to be high frequency because higher frequency results in like more range and
lower power loss,
lesser noise. Yeah, lower power loss, lesser noise.
Right.
So superposition of the message on a carrier wave. If this is a carrier wave, and then we like put a message here, like through different modes of modulation.
Okay.
So this is called modulation. Then again, we need to get back this message from this carrier wave in the final destination. So recovering the original signal from the modulated wave is called demodulation.
Correct.
So basically they are just the opposite processes of each other, modulation and demodulation. So what is the need for a modulation? The first is the frequency of the signal.
Right.
So frequency of signal, that is the message signal, is of 20 hertz to 20 kilohertz, like voice,
especially referring to voice signals.
Yeah, especially referring to voice, music and all that, the things that we can hear with our ears. So this has lesser range because this frequency is fairly low.
Right.
So have lesser range.
So if you transmit at that, there'll be too much power loss.
Yeah, it will have too much of power loss. A lot of noise might enter into this.
Right.
So
and higher frequency means lower frequency means higher wavelength. So that means larger antennas.
Larger antennas as well. So there will be a lot of different constraints.
Okay.
Here height of antenna and size of antenna are constraints. You can't have an antenna that is like say 40-50 meters, 400 meters.
In fact, I've never seen one.
Yeah. So no, we cannot have such big antennas. So to maintain the size of antennas to a fairly feasible size, we have to have a higher frequency, and for that modulation is absolutely necessary. Then there is the number of channels. This range of like frequencies is not too big, so we cannot have a lot of channels
but there might be situations in which we would need and want multiple channels.
Yeah, we'll have like for TV transmission you need as much as the number of channels possible. So for that we need a higher frequency range, like say in the order of megahertz, like multiple megahertz. For that to increase the number of channels we need to have modulation, because without modulation in this frequency range it is
I'll
not
just
possible.
elaborate on that. So when you modulate, you can vary certain parameters slightly, and that can create different channels for you. Okay.
And if it is in the order of megahertz, then there's a lot of space in the frequency range of like say a few megahertz.
Right.
So for that the number of channels can be increased.
Okay.
Next we have frequency modulation. Here the frequency of the carrier wave is modified according to the frequency of the information signal.
Okay.
So if there is a carrier wave, then there will be changes in frequency by the coming of the message wave.
Right.
So the frequencies become changed. This is known as frequency modulation or FM. Like let's say the FM radio that you hear, it's like basically frequency modulation.
Right.
Next we have the advantages of FM over AM. AM, as we already saw, it was amplitude modulation.
Okay.
In AM, most of the power is wasted in transmission because there are different wavelengths due to having different amplitudes. So the power is wasted in the transmission, and also noise is reduced due to constant amplitude in FM. If we have different amplitudes, there is a greater chance of noise entering in the system. So if in FM the amplitude is constant, the frequency is changed, so due to that the noise is reduced.
Also, the frequency being affected by the noise is like very rare and very improbable compared to the amplitude being affected by the
amplitude
noise.
Can be easily affected by external signals that creates noise in the system.
So you see, even if in a frequency modulated wave, even if noise enters and affects the amplitude, but that is not what we are concerned with. Our message lies there in the frequency.
Message lies in the frequency, and it is very hard for external sources to create any disturbances in the frequencies.
Exactly. So you would remember, while tuning those FM radios, you would sometimes want to switch to the AM versions, and it'll be so much noise, and you would
it'll have a lot of distortion in
exactly.
the AM
And as
signal.
soon as you would switch to FM, all the noise would be gone, and you would have clear channels. I think everybody has heard those. Okay.
Yeah. Next here, noise in FM can be reduced by increasing modulation factor.
Right.
So here we see that noise can basically be controlled by increasing the modulation factor.
Okay.
So MF equal to delta F divide by FM, where FM is the modulating frequency. So delta F is the range of the frequencies that are being used. So if we increase this delta F, the range of the frequencies, then we'll have lesser noise introduced in the system. So basically by varying this factor, we can reduce the noise further.
Right.
So next we move on to the sideband frequencies and the bandwidth of basically of
we
radio.
actually derived this in the
Yeah, we already saw this, but let's just have a detailed look at it.
right.
So here FC is omega c divided by twice pi. This is, as I already told you, I showed you that twice pi f is equal to omega c.
Right.
This is the angular frequency and this is the normal frequency.
Okay.
So this is a basic relation so that you do not get confused in the further study we are going to do.
Right. So when we added those the modulating component, we came across a trigonometric expression, the product of two signs, which we know from trigonometry we can write as the sum of two separate signs.
Yeah, we can write as sum of sines and cos
or cosines actually.
Cosines,
So from there we get two expressions, and those two different terms have these frequencies, FC plus FM, which is the sum of carrier frequency and the modulating frequency.
So in that topic I wrote it as omega c plus omega m,
right,
and omega c minus omega m.
Okay.
So these two can be broken into FC plus FM and FC minus
it's
FM
just
by
the angular
this.
frequency, and this is the frequency.
It is easily converted to the normal frequency.
Right.
So upper sideband frequency is this, and the lower sideband frequency is this, as I already showed using omega terms.
Right. Upper sideband and lower sideband are slightly new terms for you. I get it, but these are terms that you need to get used to, and they don't have any complicated meaning. They're just the sidebands that arise when you modulate a signal.
Yeah.
And you can easily see in the math that these two terms arise there.
Yeah, because of the introduction of FM, this FM term.
Right.
This is added, so frequency increases here. So this is the upper sideband. The lower sideband here, it is subtracted, so it has a lesser frequency, so the lower sideband.
Right.
So basically these are not too difficult. Just simply you need to remember upper is due to adding of the message, lower is due to subtracting of the message frequency.
Right.
Bandwidth, as I already told before, it is FC plus FM minus FC minus FM. So difference between the upper sideband and lower sideband frequencies, which results in 2FM, that is twice the frequency of the modulating signal.
Right. And obviously this is independent of the carrier frequency, because
bandwidth is generally independent of the carrier frequency. It depends only on the frequency of the message that we are using.
Okay.
Next we have the power and current relations in amplitude modulated wave. So average power in unmodulated wave. I am stressing the fact unmodulated.
Right.
Here the message has not been modulated onto the carrier frequency, carrier wave. So the power of the carrier wave equals to AC divided by twice R. Here AC is the amplitude of the carrier and twice R is the resistance that is used in the circuit of the transmitter.
Okay.
So this is the average power. So next we have the total power in modulated wave. In modulated wave is after the message signal has been incorporated into the carrier wave.
Right.
So here we have power PT equals to PC 1 plus m square by 2.
Right.
So m is the modulation index, or the modulation factor, if you would like to say that way. So PC is this power of the carrier wave, and PT is the net power, total power.
Right.
So the ratio is PT by PC equals to 1 plus m square by 2.
Right. And the formula makes sense because since m was the ratio of amplitudes, obviously m square would kind of be the ratio of power.
Because we know that power is like basically the square of the amplitude. And
so you can check there, and the rest of that, how that comes, is not really our concern right now.
Yeah, because these formula can be directly used to solve the problem. So you are supposed to like look into this formula and try to remember them,
Right.
and keep them on your fingertips, because if the question comes and you can directly apply in this formula,
Okay.
it will be like faster and easy marks for you.
Right.
So next we see total power equals to I square total multiplied by resistance. This is what we get from current electricity
Okay.
chapter.
So here PT is the power transmitted.
The total power, yeah.
Okay. Oh, total power actually.
Yeah, total
Okay.
power, that is also, you can say, the power transmitted, because the total power is the power of the transmitted wave, the
Okay.
modulated wave. So
Right.
that is what to transmit. And PC is IC square into R. This is basic relation from your current electricity.
Exactly.
So we have the ratio here, IT by IC equals to root over M square by 2.
Okay, so that's an important relation between between that, as you saw, the ratio of amplitude is simply M, and the ratio of powers comes out to be in terms of M square, and IT by IC, the total current by the carrier current, that ratio comes out to be the square root of 1 plus M square by 2.
Yeah. So here you see that the ratio of the total power by the carrier power does not depend on the resistance of the circuit.
Right.
So
In fact, this ratio is simply the square root of the ratio of those two powers.
square root of the powers. Yeah.
Right.
The resistance does not come into effect in this formula.
Okay. And please note that if this was, this is I total by I carrier. If it was I modulating by I carrier, this expression would be simpler, and this one would not be there. So
Yeah.
that you can figure out, it's just basic manipulation. So
Yeah.
here we just saw what modulation and demodulation means, and what is the need for it. Power loss, to prevent power loss, and to have reasonable sizes of antennas. After that, we saw what advantages of FM over AM were, and then we moved on to discuss about sideband frequencies and the power and current relations in AM waves. So this was modulation.
So next we move on to a block diagram showing the basic elements of a communication system. So first we have here the information source. So what we have is a source of information that generates the signal. Next it is given to a transmitter,
Right.
so that there is encoding and modulation. That
So
is-
at this step, we modulate.
yeah, we modulate it and then we transmit it via transmitter.
Right.
And the channel, that is basically our atmosphere, it travels through this channel.
Okay.
In the meantime, some noise may be introduced.
Okay,
Noise
the
is-
channel might be a cable, it might be space,
Yes,
it
but
can
since
be a
we're
fiber
talk-
optic cable.
Yeah, it can be all those, but since we're talking about this communication system using ground waves,
Right.
direct
So
waves,
it'll
and
mostly
sky
be
waves,
space.
yeah, it will mostly be the atmosphere.
Yeah.
But keep in mind that it can also be like, say, optical cables or like any wires and all that.
Right.
So in every communication channel, some amount of noise would be introduced in this channel. Then it is received by a receiver at the opposite end.
Right.
So then there is some decoding and demodulation. That
Okay.
is basically the reverse of encoding and modulation.
Right.
And distortion would be there due to this noise introduced and some lower efficiency of like demodulation and all
Exactly.
this
So
stuff.
when we receive distortion is the net, deviation from what
Yeah.
we were supposed to receive that we detect.
We never receive something that is exactly equal to what we wanted to send.
Yo.
So there will be some amount of distortion.
Okay.
Obviously there will be, and some amount of noise is always introduced in the channel, because nothing can be 100% efficient, or it is not an ideal system.
Right.
In ideal system there will be no noise and no distortion,
Okay.
but since it is not an ideal system, there will be always some amount of distortion and some amount of noise would always be introduced into the channel. And this after this is received by the receiver and it is decoded, it is given to the destination, that is the person who wants to receive this message. So this block diagram is fairly important for mainly your board exams, because in that they might just
remove that.
this.
Exactly.
They
And
might
ask you to,
remove this. They might just ask you, fill this up.
exactly.
Or they might remove
Especially
this.
noise. Yeah, I've seen that
Yeah.
question a lot, in fact.
That this noise thing is always removed, and people think what is coming from outside, I don't know, and all that. So you need to remember these terms properly and the order in which they come, because if you do not remember the order and you remember the terms, you might get confused if these arrows are changed.
Right, the order actually makes logical sense. There's
Yeah.
nothing you have to remember here. You have to just understand, look, and
If
be
you
familiar
look
with.
at if you look at it logically, you'll get to know that after the information source, obviously the transmitter is going to come,
Right.
then the channel, then receiver, and the final destination.
Okay.
They might just remove this and send an arrow here
Right.
and an arrow here, and they'll give you A, B, C. You have
Okay.
to choose which is, like, they'll remove these names or change something, and then there are a lot of possibilities in this question.
Exactly.
So you have to, like, get this into your head, and it is fairly logical and very easy to remember. So you do
Okay.
not need to put a lot of effort into it. Just look at it logically and you'll get to know.
Okay, so that was a block diagram of a typical communication system, and we discussed the components here. We discussed about the encoding and the decoding or modulation or demodulation that will happen at transmitting and receiving ends, and we also talked about noise that will be pumped into the channel no matter what we do. So that was a typical communication system. Right, so we'll begin with problems for the chapter communication systems, and here's the first problem. It says, for skywave propagation of 10 megahertz signal, what should be the minimum electron density of the ionosphere? So we obviously know that what frequencies we can reflect back from the ionosphere depends on the electron density. So it asks, if we are given a frequency and we are asked what will the minimum electron density be.
Yeah, so here in this problem we can basically set this directly into the formula that I've given in the theory part.
Right.
So for this you need to remember the formula,
Okay.
that the critical frequency Fc equals to 9 into root over n.
Okay.
Here n is the electron density of the ionosphere.
Right.
So when n is the electron density and Fc is the critical frequency, we can put this Fc directly into 10 megahertz.
Right.
So first let's simplify this equation so that n comes to the left hand side.
Okay.
So having this, n
It will
equals
simply
to
be Fc square by 81.
Fc square by 81.
Correct.
81 is 9 square. So put this Fc 10 into 10 to the power 6. You're supposed to put this 10 to the power 6 because it is in megahertz.
Right.
It is like 10 to the power 6 hertz.
Okay.
So
Square by
this
81.
divide by 81,
Right.
which gives the answer nearly equals to 1.2 into 10 to the power 12 per meter cube.
Okay.
So here per meter cube is because the number density of the electrons in the ionosphere.
Okay.
So this is like 1.2 into 10 to the power 12 electrons per meter cube.
Okay.
So which is the final answer.
Right. So that was problem 1. We were given a frequency and we were asked to find the minimum electron density of the ionosphere in order for that frequency to be reflected back.
Yeah.
Okay. So we'll move on to the next problem. How many 600 kilohertz waves can be on a 5-mile transmission line simultaneously? So, okay, not a lot of information given there, but I think there's enough. And we are given we are given the frequency of all those waves to be 600 kilohertz, and we're given the transmission line to be 5 miles long.
Yeah.
Okay.
So here we have a 5 mile long wire.
Right.
So line is basically a transmission line is
Right.
basically a wire.
Okay.
So let's assume that this is of 5 miles.
Okay.
So what we have here is 600 kilohertz is the frequency of the waves. So F equals to 600 kilohertz
Right.
and D equals to 5 miles.
Okay.
So what we see here is we need the wavelength because frequency in itself is not related to any distance. So if there is a distance, so we need to calculate the wavelength.
Right.
So wavelength equals to C by F. So C is the speed of light in vacuum and F is the frequency.
Right.
So speed of light, as you all know, is 3 into 10 to the power 8 meter per second.
Right.
But here we are given distance in miles and we do not directly know the transformation from like meters to miles. So here is another standard value. It is 186,000 miles per second.
Okay.
So this is the speed of light in vacuum,
Right.
like C. So we have this in miles per second. So we can simply put this, substitute here 186,000 divide by the frequency, that is 600 kilohertz. So 600 into 10 to the power 3,
Right.
which gives us 0.31 miles.
Okay. So we just found out the wavelength.
Yeah, we found out the wavelength. So next we have to find out the number of waves. So the number of waves is directly like the number of wavelengths.
Okay.
So if this is the wavelength, this is equal to one wave.
So we can obviously take the ratio of 5 mile and
n
1
equals to d by lambda. So for one, like, it is the distance, total distance divided by the wavelength of one wave. So which gives us, basically substitute this and we get the value as 16.13. So this we can basically assume that 16 total waves can be on this 5 mile transmission line simultaneously.
Right.
Like this, there will be 16 waves total.
Okay. So that was problem 2. We were given a frequency and asked how many of those waves can be on a transmission line of a given length. So what we proceeded to do was calculate the lambda from we know the speed of electromagnetic radiation or light to be 3 into 10 raised to 8 meter per second, and it's a very useful thing to remember here that 186,000 miles per second can also be used to represent speed of light, and using that makes us reduce our work. We don't have to convert, and it's usually those conversions will be inaccurate and they'll take time. Also, most people will not remember the ratios, so instead of that we can simply remember this value and use it when we need. So we found out the wavelength to be around 0.31 miles, and then we simply had to divide 5 miles by 0.31 miles to get the number of waves on this transmission line. So this says that an 80 megahertz carrier is modulated by 400 hertz sine wave. The carrier voltage is 50 volts. So we are given the frequency, the carrier frequency, and we are also given the modulating frequency, and also we have the voltage, the carrier voltage at 50 volts, and the frequency deviation to be 20 kilohertz. So we need to find the modulation index. Fairly simple, I guess.
Yeah, the question is really simple, but here there's a lot of unnecessary info.
Okay.
So you might get confused which formula to use. You have something of voltage,
Right.
and you have something of the carrier frequency as well,
Right.
and you have something of the modulating frequency.
Okay.
So it's 80 megahertz here, 400 hertz here, 50 volts here, and then also the 20 kilohertz of frequency deviation is given.
Okay.
So here you need to know which formula to apply, because there are a lot of formulas relating to the modulation index. So here you need to find out which are the values that you really require and which you need to ignore.
Okay.
So let's see the most easiest formula for relating the frequency deviation and the frequency of the sine wave here, modulating wave. So we get that MF equals to delta divided by FM. Here delta is given as 20 kilohertz, FM is the frequency of the modulating wave.
Okay. So what we are basically saying that this is frequency modulation. So we actually
this delta you can also represent as delta F.
Right. So an important thing to note here is that the question doesn't actually say anything about the kind of modulation. You have to look at it and conclude that this is frequency modulation. And if that is the case, obviously the modulating,
because the frequency deviation is given, so it is obviously you can make out from here that is FM wave.
So if it is FM, we can obviously relate the modulating index to the frequency deviation and the carrier frequency.
So here the frequency deviation delta F divided by FM. Please note this is not multiplication, I'm just representing it in different ways. You can write this delta or this delta F.
Okay.
So it is equal to 20,000 because it is kilohertz divided by 400, which is in hertz.
Right.
So this is fairly simple. You get it as 50. So 50 is the modulation index, and you do not need all these values like 80 megahertz or 50 volts. You get this from like the frequency deviation 20 kilohertz and 400 hertz of the modulating sine wave.
Right. So this
yeah.
was problem 3, and you noticed how there was some unnecessary information there, which is often the case, in many physics problems to all of such chapters such as communication systems and
because
electromagnetic waves.
there are not many things that you can change in these formulas, so they just give you unnecessary information basically to make you confused.
Also, if you see too much information in a question like this, please remember that mostly all of it will never be used, because nobody wants you to remember huge formulae and they sit in interest examination. The point there is always to test your concept and how you can work with them. So we'll look at problem 4 now, and this one says that a transmitter radiates 12 kilowatts power at 80% modulation index. So here obviously we need to find a relation. We need to somehow relate the power, the radiated power, to the modulation index.
Yeah.
Okay.
So here you should remember I gave the formula that the power total divided by the power carrier.
Okay.
So PT divided by PC is equals to 1 plus m square by 2.
Correct.
So m is the modulation index.
Right.
So with some simplifications and just taking to the other side, you get PC equals to PT divided by 1 plus m square by 2.
Correct.
So here you can basically substitute, because the power total or the transmitter radiated power is given and the modulation index. So it is fairly easy to find PC just by substituting the values.
Right.
So here you have 12 kilowatt, and then you have this as 1 plus, since it is 80%, it is 0.80 divided by 2, and you square this value.
Okay.
So
this comes out to be?
This comes out to be 9.09 kilowatts.
Okay.
Which is the required answer.
Right. So here again we were given the transmitted power, and we were given the modulation index, and we were asked to find the power in the carrier. So obviously we are familiar with this relation: power transmitted by power carried. Okay.
Yeah.
So the carrier power is PC, and is obviously equal to 1 plus m square by 2. We studied that in theory. So again you can just substitute value and get the answer after that. And so that was problem 4, and we'll look at the next one now.